The concept of a multiverse, frequently featured in movies, might be quite familiar to most of us. However, what we commonly refer to as the multiverse is actually just one type of many possible universes, parallel universes, to be precise. The idea of multiple universes isn't just a singular hypothesis in physics. Notable American physicist Brian Greene discusses various types such as cyclic multiverses and landscape multiverses in his book, The Hidden Reality. Moreover, Max Tegmark, a physicist at MIT known as a leading figure in multiverse theories, categorized these into a 4-level classification in his January 2003 paper titled Parallel Universes. Today, I want to discuss these multiverse levels and the rationale behind these hypotheses, starting from level 1 to 4. Level 1, Quilted Multiverse. The term quilted refers to the process of stitching together small pieces of fabric, often creating a pattern that repeats. If the universe is indeed infinite, it suggests that similar universes may occur repeatedly, like patterns in quilted fabric, resembling rows of egg cartons. This hypothesis begins with what we call the observational limit. We observe the universe through light, which, despite its speed, is not infinite. Thus, we can only observe as far as light reaches, what we call the observable universe. The edge of this observable range forms what's known as the cosmic horizon. Beyond this horizon lies an unobservable darkness. However, it's reasonable to predict that the universe extends beyond this boundary. Imagining a universe that ends precisely at this boundary seems more unnatural than one that continues. Scientists like Tegmark have tried to calculate just how large the universe would need to be for there to be an identical configuration of particles as ours, suggesting that a universe repeating in such a manner would statistically include one identical to our own. An intuitive analogy: imagine a concert where Taylor Swift and the audience each hold cards numbered 1 to 7. Everyone arranges their cards in a sequence, like 1, 2, 3, 4, 5, 6.7, or any other combination. If there are 50-40 spectators, statistically, at least one will have arranged their cards in the same order as Taylor Swift. As the number of spectators increases by multiples of 50-40, so do the chances of matching Taylor Swift's sequence. This concept is similar to the quilted multiverse theory, which is supported by observations from the WMAP satellite, suggesting the universe is uniformly filled, implying a much larger cosmos. However, some argue that identical particle arrangements do not necessarily mean identical universes. This type of multiverse assumes the same physical laws apply beyond our observational range. Level 2, Inflationary Multiverse. As suggested by its name, this theory stems from the inflation theory, an enhancement of the Big Bang theory. The universe started from a point of infinite density and experienced rapid expansion early on. This expansion, driven by a repulsive force generated by a field filled with inflaton particles, caused the universe to expand about 1,000 times in a tiny fraction of a second. The inflation theory, which continues to be highly regarded for explaining the origins of the universe, suggests that inflation wasn't a singular event, but an ongoing process. The quantum uncertainty inherent in the inflaton particles means that after initial inflation, the energy state of the inflaton field fluctuates wildly, leading to new inflations and thus new universes. This ongoing creation of universes might resemble a foamy bubble bath, and since these universes could have begun under different conditions, they might operate under different physical laws. Unlike Level 1 universes, which might eventually be observable as our technology advances, Level 2 universes, due to their distinct origins and expansions, would remain unobservable. Level 3, Quantum Multiverse. Derived from the many worlds interpretation of quantum mechanics, the quantum multiverse suggests that every possible outcome dictated by quantum mechanics is being realized in various parallel universes. This might seem far-fetched, but it's a legitimate interpretation stemming from quantum mechanics' foundational principles. Niels Bohr once described particles as displaying wave-like characteristics when not observed but behaving like particles once observed, a concept known as the Copenhagen interpretation. However, Hugh Everett proposed that the wave function does not collapse. Instead, every possible outcome splits off into its own universe. For instance, if a cat is placed in a box with a mechanism to release poison gas after an hour, the universe splits into one where the cat is alive, and one where it is dead when the box is opened. The quantum multiverse is a popular concept in films, and is fascinating but remains unprovable since we cannot feel or observe these splits. Level 4, Mathematical Multiverse. This hypothesis suggests that every conceivable universe that can be mathematically formulated actually exists. We use physics to understand the world, employing mathematics as a tool. However, this might be backwards. Perhaps we didn't invent mathematics, but discovered it as a pre-existing aspect of nature. The laws of the world fit so precisely into mathematical models that it led scientists to speculate that perhaps mathematics is not just a tool, but the essence of the universe. This concept was further supported when Dmitri Mendeleev's periodic table, initially with many gaps, predicted elements that were later discovered filling those gaps. Galileo even stated, "The book of nature is written in the language of mathematics." This view raises the possibility that our world might be akin to a simulated reality, operating on mathematical and physical rules. Because simulation itself is predicated on mathematical and physical laws, the concept of a mathematical multiverse aligns perfectly with the idea of a very mathematical world. Could our world actually be a simulation? Do multiverses truly exist? The answer from scientists remains divided, as science itself is inherently conservative and strict. Science requires that phenomena be observable and hypotheses verifiable through experiments and replication before they can be accepted as theories. Since the multiverse theory inherently implies that it may be unobservable, proving it is challenging. For this reason, some scientists argue that the multiverse theory is futile. Personally, I agree that if a hypothesis cannot be proven, it cannot become a theory. However, I also believe that it is not entirely useless. Stephen Hawking, in his last book, Brief Answers to the Big Questions, conveyed a message to never fear proposing ideas or hypotheses, no matter how foolish they might seem. Such challenging hypotheses may indeed be the seeds for monumental discoveries in the future. Copernicus's heliocentric theory initially sounded insane, but brought about a Copernican revolution, later validated by Galileo, Kepler, and Newton. Perhaps the multiverse theory is suggesting once again that our universe might not be the center of everything. Thank you for watching. This has been the Fun Science Channel, All is Science.